Good evening, everyone. Welcome to what is our last Fireside chat of 2025 with me, Dr. Binita Kane, and my co-host.
Helen Oakleigh, hi. Filmmaker, co-host and representing the charity Long COVID Support.
And so this is part of our Fireside chat series from our YouTube channel, which is called the Long COVID Clinic, What You Can Do, where we are trying to spread really good information about research, treatments, and keep you guys up to speed with what's happening. As usual, we are live and interactive, so please do use the chat for your comments and questions, and Helen will be diligently backstage keeping an eye on things, and we will try and get through as many questions as possible before the end of the session. So with no further ado, I will pop you backstage, Helen, and
see you shortly.
Yeah, see you shortly. And I would like to introduce my fabulous guest for this evening, Professor and Dr. Klaus Wirth, who is a German physician, professor of pharmacology and biotech entrepreneur with now decades of experience spanning both academic medicine and the pharmaceutical industry. He's lectured at university in Frankfurt and is also the co-founder of Mitochondria, where he focuses on translational approaches to both muscle and mitochondrial dysfunction. Since 2018, Prof. Wirth has been a leading contributor to the ME/CFS literature and more recently, long COVID research. Thank you so much for joining me this evening, Klaus, all the way from Germany. Really appreciate you being here.
Good evening, everybody.
Yeah, and so I always like to start by just asking guests to say a few words about themselves and why and how you got interested in ME/CFS, because we love people who are interested in researching this condition, but it's a lonely world out there, isn't it?
Yeah, so I'm a medical doctor by training, and I spent 37 years in drug research, most of the time at Sanofi in close to Frankfurt. I worked on many diseases and organs in these 37 years. So I think this is really necessary for understanding such a complex and multi-organ disease like ME/CFS. 6 years ago, I became interested in ME/CFS only by chance. I saw a report on TV on a young man, 19 years old, who suddenly got bedridden by ME/CFS. And I made a Google research to find out what ME/CFS is. And the next day, I went into the database PubMed and I saw a paper of Carmen Scheibenbogen from Berlin, who mentioned autoantibodies against the beta-2 adrenergic receptor. And immediately I had the feeling that I could understand aspects of the disease because I worked on this beta-2 adrenergic receptor. And I investigated the effect of this beta receptor or simulation of the beta receptor on its blockade on cerebral blood flow and also on skeletal muscle blood flow. And you know, there is central fatigue and there's muscle fatigue, and this is certainly related to perfusion. And this is how my interest was stimulated.
Yeah, no, thank you. So, you know, it's really interesting that you're quite an unusual researcher in that you've got experience of looking at muscle across lots and blood flow across lots of different organs. By the way, I've just been alerted to the fact that the comments are not just turned on at the moment, so slight technical issue. And we're just looking into that, and we'll try and switch those on as soon as possible, guys. I'm really sorry about that. Yeah, so Klaus, we've talked a little bit about how to start tackling the topic of your research because it is quite complex. There's lots of physiology involved, and you know, I'd really like people to understand this as much as possible who aren't scientists. So one of the ways I think about ME is that there is a problem with oxygen getting into cells, and there's a problem with cells using oxygen. So I try and think about how does oxygen get from the air through the lungs, through the blood vessels, into the cells and into the mitochondria, which are the little organelles within the cells that make the energy. So should we start with blood flow? Because clearly the blood flow to the organs is really, really important to deliver the oxygen. And we know that blood flow can be impacted in lots of ways in ME. Do you want to just talk us through that a little bit?
Yeah, there is a severe perfusion problem, and at different levels. It's a combination of disturbances. None of this disturbance is so severe that you can say this is the only cause. It's the interaction of a number of disturbances of the heart, of the large blood vessels, of the filling of the blood vessels, of the capillaries, and it ends up in a problem of oxygen and nutrient supply to the skeletal muscle. And in the long term, this changes the ionic condition and ion transporters, so that the new disturbance appears and that mitochondria are damaged. So it starts with a blood flow problem that has so many facets and so many causes and so many interactions from the heart to the capillaries. Particularly in long COVID, this is a microvascular disturbance, but you also find cardiac disturbances, and you find that the blood vessels are not really filled. They're not really filled. It's called hypovolemia, and they do not contract appropriately to fill the heart, to cause so-called preload of the heart. So all this ends up in a reduced perfusion of muscles, and this causes over time then secondary changes that fix the disease. This causes then mitochondrial dysfunction, and this reinforces all the problems.
Yeah. So just for me to go over that, there's actually problems with the way that the heart pumps blood around the body. Sometimes if people have POTS and orthostatic intolerance, there's also problems with flow through the blood vessels and how the blood vessels are regulated. And also problems with the little micro capillaries, which, we know there's changes. So, and I think what you said there was that when the perfusion or the flow of blood to the organs is reduced, then that affects the function of the mitochondria. So let's get into that a little bit more. We'll maybe come back to blood flow a bit later. So you've done quite a number of years of research, and you've come up with a hypothesis which could potentially explain this whole unifying hypothesis of what is going on in every patient with ME. And it is still a hypothesis, it's not fully proven yet, but can you talk us through that?
Yeah, the perfusion disturbance normally leads to glycolytic metabolism, which there's a lack of oxygen, and then there is glycolysis, and this is associated with the production of acid and protons. And the protons, they are exchanged against sodium. There's these do not diffuse freely to the cell wall. So there is.
Hang on, Klaus, I'm just gonna stop you there, because there's lots of words there that I don't think our audience will necessarily understand.
Yeah.
So can we just go back to, so I think we're talking a little bit about how certain things like sodium and potassium and calcium, these salts that are in the blood, get into cells. So are we talking about these are little pumps that are on the outside of the mitochondria? Is that what you're talking about, or are they on the outside of cells?
Outside the cell, and
These
also
pumps.
The mitochondria also has pumps. It also has the calcium pump.
So
these pumps.
When it's working properly, what should the pumps be doing in a normal functioning cell?
Yeah, the pump should pump out the sodium. Sodium enters the cell by excitation, by ion channels during when you stimulate the muscle for muscle work, and also by ion transporter, for instance, the exchange of protons, which means acid against sodium. So there is a sodium loading in the cell. There's sodium loading, and sodium gets too high, and we know this from the heart and from other circumstances. This is harmful. Too much sodium in the cell does harm, because at a certain point this has effects on intracellular calcium. Calcium is so important also for the mitochondria. They are stimulated by calcium, but it can be too much. There's an optimum. And when the mitochondria receive too much calcium, they get damaged. And too much calcium rises too much. When sodium rises gets too high, because there is a pump, a sodium calcium pump in the cell membrane, and normally it pumps out calcium that enters via the calcium channels in exchange for sodium. But at high intracellular sodium, the pump changes in direction, and instead of pumping calcium out, it pumps calcium in, and then you get the overload. So the sequence is perfusion low, and then you get more sodium, and then with more sodium you get more calcium, and the mitochondria are damaged. So this perfusion is not the only problem, but this sodium pump, the sodium potassium pump, which reduces pumps potassium out, which pumps sodium out, is too weak. During exercise it must be stimulated, and it's not sufficiently stimulated during exercise because it requires stimulation by the beta-2 receptor, and many patients have autoantibodies against this. So this receptor does not work properly, and so the sodium pump is not stimulated. So sodium rises, and when sodium rises, calcium rises and makes the damage. And the second cause for...
So I'm just going to stop you again. So and people may not understand the ins and outs of this exactly, but I think what we're saying is there is this pump that's on the edge of cells. It's also in the mitochondria, and its job is to control how much sodium is being pumped out and calcium is being pumped in. But when you have problems with the blood flow to the cells, this can affect the functioning of these pumps, and you can get too much sodium being pumped out, and then you can get overload of calcium inside the cell. Is that a fair summary?
Yes. There are two causes for sodium load. It's the reduced perfusion, which makes acidotic metabolism, and it's the function of the pump itself, which is disturbed. It's unrelated to perfusion. It's simply that the beta-2 receptor doesn't work and doesn't stimulate a pump. And the second cause is...
So let's talk about because we're talking about beta-2 receptors. I just think we need to explain that. So beta-2 receptors are these switches that are on the outside of, they're on blood vessels basically, and they help control the size of blood vessels. So sometimes you need more blood flow to organs, and sometimes you need less blood flow. And so exercise when we say exercise in ME, by the way, we mean any sort of exertion. Exertion is a state where you need more blood flowing to the muscles and the organs and the tissues. So what you're saying is that these beta-2 receptors are faulty. They have lots of functions. So they regulate how much blood is flowing into the organs, but also they have an influence on these sodium pumps. Yeah. So now we've got these two main sort of reasons why people are getting faulty sodium pumps. Firstly, there's not enough blood going into the organs. And secondly, you've got these faulty switches. And then what happens is the pumps reverse and they do the opposite of what they should be doing. And you get this buildup of calcium inside the cells, which means and then that damages the mitochondria. Is that right? Have I got that right? Because
that's right. This receptor is so important for exercise, also for the blood flow of the heart, for blood flow of the brain, and for blood flow of skeletal muscle, and for the sodium pump in skeletal muscle, and also for the bronchi, it's also very important. So it can be called an exercise receptor. You need really this receptor for performing muscle work. And if it doesn't work, you cannot exercise. You cannot perform muscle work.
Yeah, and I think one of the things that you were saying to me when we were chatting before the session is there definitely seems to be a threshold at which the pump switches. So there's like a threshold of exertion, just like we talk about. And you think this is the PEM threshold, so the threshold above which people are going to start developing post-exertional malaise, or PEM, in ME is related to when this sodium pump switches. That's one of the things it can be related to. Yeah,
exactly. This is a biological correlate. So you have the clinical PEM threshold, and we think there is a biological correlate, a true threshold. It's the moment when this transporter, the sodium calcium exchanger, changes its direction because the sodium is too high. So it's related to a sodium concentration. If you're above the threshold, then the exchanger switches its transport direction, and then this causes mitochondrial damage. And the mitochondrial damage is, for me, it causes a PEM.
Yeah. By the way, everyone, the chat is now working. Sorry about that, but obviously a few people have discovered it because the comments are coming in. Do keep them coming. So this concept, Klaus, because I think we've known for some time about lactate threshold and PEM, and when people get into a state where the oxygen supply is being outstripped by the demand, so they're exerting themselves and there isn't enough oxygen getting to the tissues, because obviously we can't store oxygen in the body, we know that the cells switch into this kind of non-oxygen pathway, and that produces lactic acid. We call that a lactate threshold. And that's what we, very traditionally in my patients, we're trying to keep them strictly below this lactate threshold, so that they're not exacerbating PEM, and it gives them a chance of recovery. The sodium threshold is not something I've thought about really in my clinical practice, because we can't really measure it at the moment, can we? Not in a clinical setting. How have you done those experiments then, where you've looked at that threshold of the sodium, like very simply?
No, it's really this is really known from physiology in also in other organs. This sodium calcium exchanger has a threshold. This is so well established for now 40 years.
Okay.
So yeah.
How do you measure that? Do you physically, do you
in
measure
experiments?
that?
This is really done. Then it's really experiments. This is really only in experiments. You cannot measure it clinically. It's really in cell experiments that it's measured.
So this would be, you'd be taking muscle biopsies or tissue samples?
Yeah, it can be shown in many tissues and in many cells. Also in neurons, it's also a major cause of cell death, neuronal death, calcium overload by sodium overload. So this is a very old concept, and this can be shown in the heart too. For instance, in the so-called ischemia reperfusion damage, it's the mechanism. This is the mechanism behind.
Yeah. So you see this in other conditions where muscle is affected, basically.
Yeah.
So just taking it back to the patients and this idea of PEM, and one of the things that we really aspire to when we're seeing our patients is trying to get people to a period of stability for 3-4 months where they have got no PEM, because they are pacing so strictly based on scientific principles. And we say once you've got to that baseline, you can start to sort of recover. From your perspective, from your research, what happens if people keep going over the PEM threshold, exacerbating PEM? What do you see a worsening of the underlying? Can you explain why overexertion leads to that catastrophic decline sometimes in patients?
Yeah, with every PEM, there's calcium overload and mitochondria are damaged. And with damage of mitochondria, you have this more anaerobic metabolism. So we have more lactate, more acid, more sodium overload. And then there's a vicious circle which worsens everything. So you have to avoid PEM because you have to avoid mitochondrial damage. Because with every mitochondrial damage, you reduce the pool of intact mitochondria, and you need them, of course, for getting energy, and you need them also for recovery. So the more mitochondria are damaged, the more difficult is it to recover. I mean, you have to stop the damage that the mitochondria can recover spontaneously, but this takes time. And the less you have, the more difficult is it to recover.
So it's that vicious circle that you were talking about. So the more PEM, the more inflammation, the more lactic acidosis, the more sodium, calcium, and then the more damage, and then it's a spiral.
You can't get out of it.
Yeah, and so this it's so important as a concept for people who are trying to recover from this really horrible illness to avoid PEM, and to really, and we've done another video on micro-pacing with Robin McNellis, which is one of the most popular ones and probably one of the most game-changing ones for my patients. If you haven't seen that and you have long COVID or ME, please go and watch that, and the talk with Todd Davenport as well, because we really talk through some of these concepts about pacing. But I think it's another reason why graded exercise should be absolutely discouraged, Klaus, if people genuinely have true PEM, they have true ME. What do you think about graded exercise as a treatment?
No, one should always remain below the threshold, but the threshold is probably not fixed, so you don't know exactly where it is, so one has to be extremely cautious. It's really, as soon as the patient feels more energy, it's really tempting to use it. I mean, but the consequence is the next PEM, so the PEM is somewhat higher, but if you exercise, do more, it's certain that you get damage again. So
yeah,
one has
and it
to
is hard.
be extremely disciplined. I think I know this is extremely difficult. If you feel somewhat better, you try to use it, but you shouldn't, for at least for a while.
Yeah, and I think that's another key concept, that as you start feeling better and getting more energy, it's almost more important to row back at that time and not overspend. I sometimes use this analogy of energy is money, and you're trying to save up to buy a house or a car. And if each time you get into some, healthy looking bank balance, you just overspend and get into debt, you have to then spend that time rebuilding back to baseline, back to zero, before you can start improving. And so that, it's that boom bust. So, I think that concept is one that just isn't pushed hard enough in a lot of traditional models of ME care, which still do encourage graded exercise. So it's very challenging. It's very challenging for patients because we don't have amazing tools. We've got some really good tools like Visible and other wearables, but we don't have amazing tools to really scientifically pace. But yeah, okay. Well, in the pipeline, then, if you're a drug developer, aren't you? You're someone who spent 40 years in the pharmaceutical industry, and that's what you do. You develop drugs in the pipeline. What sort of drugs do you think could help in this situation of this sodium and of this calcium overload in the cells?
Our drug stimulates the sodium pump in a way that replaces the beta-2 receptor, and by that prevents sodium and calcium overload. And additionally, it improves perfusion of the brain and the skeletal muscle. So it addresses the mechanisms of damage and the mechanism of PEM. So it focuses on the cardinal symptoms of exercise intolerance and PEM by interfering with this perfusion and these ion transporter disturbances. So it corrects the disturbance of the ion, of the ion transporter, so that there is no sodium overload and no calcium overload.
So, and that's a drug that is actually in development at the moment?
Yeah, this is in preclinical development. It has not yet reached the patient, and we have to perform toxicology studies and all the preclinical requirements for being able and being allowed to go to the human.
And I think it's important for the community to have some hope that there are some new drugs in the pipeline. And I know you can't give us too many details about it at this moment in time, but your company is actually developing something to tackle this specific problem with the sodium calcium pump. Yeah. And go on. And the German government has just announced some funding, haven't they?
Yeah, it's just 50 million euro per year for 10 years. It's called the National Decade Against Post-Viral Diseases.
Yeah, and how's that money being distributed at the moment? Is it competitive grants? Do people like yourself have to apply?
Yeah, this is just discussed. This is under discussion. There was a discussion in the German Parliament today, and this will be then decided during the next month. And I hope that they will also support drug research. I think this is so important, because drug research not only leads to new drugs and of course for treatment, but drug research is also important for basic research and clinical research, because at a certain point in time, you have, in every disease, you have several hypotheses. And you cannot resolve this by more incremental recognitions by basic research, normally not. Then if you have a drug that is derived from a disease concept, and you test it, an agent, I call it an agent, and it works, the hypothesis is proven, or it doesn't work, it can be disproven. So it's so important to have drugs early in research to decide on whether the hypothesis is true or not. So research, clinical basic research and drug research have to be done in parallel. And the drug research is a very important instrument in clinical and basic research to find out the truth, which hypothesis is true or which is wrong.
Yeah, and certainly in the UK at the moment, we haven't got a cohesive one group that's leading all the, we don't have kind of a consortium or a collaboration of different groups who are leading the research. It's still kind of quite siloed and in different pockets. So I'm really hoping Germany can get itself together and do something better than what we're doing in the UK.
Yeah. I mean, it's important now to allocate the money reasonably to different fields, to clinical research, to drug research, to patient research.
Yeah. Okay. We've got quite a few questions coming in. So what I might do is get Helen back on the screen a little bit earlier than usual, but I think that's okay. And start maybe answering some of the questions that are coming in through the chat. Hi, Helen.
Caught me off guard. There we go.
Sorry, I popped on a little bit earlier than usual, but I thought we'd actually dedicate some time to the discussion.
Yeah, no, absolutely. Thanks so much for the questions, everyone. Sorry about the tech issue at the beginning there. Yeah, lots of varied questions actually, and some we've covered, some we haven't. Where to begin? let's start with this one that just came in.
Yeah, go on, Helen.
I just wanted to jump in. No, really interesting one just came in, and then we'll work our way back, I think. How does this interact with the immune system? Does this theory work with? Oh, you've put it up.
Yeah.
I don't know how to pronounce that actually. How do you pronounce that word?
Itaconate, I think.
Okay. Shunt theory from Ron Davis from Stanford.
I mean, the immune system plays a strong role because of the autoantibodies, but I think only half of the patient has autoantibodies. So we have to explain how ME/CFS in those who don't have these autoantibodies, and it's part of our unifying hypothesis. But there are autoantibodies against a number of structures. It's not only a beta-2 receptor, it's the alpha-1 receptors. It's the alpha-2 receptor. It's an ion transporter. It's against structures that produce GABA in the brain and so on. So there are numerous autoantibodies, and it's not a single one that determines the pathophysiology. So concerning the itaconate shunt, I cannot reconcile it with the itaconate shunt, and there's no proof of this. This was an idea that has expressed at a single time, but there is no work on it, so I cannot really judge it.
Fair.
Just for people who don't know what the itaconate shunt is, I've just asked for a simple explanation. So essentially, it's when immune cells detect danger and they deliberately change how they use energy so they can fight the infection and limit the damage. So instead of running their sort of normal energy cycle efficiently, they can divert part of it to make this special molecule called itaconate. And that can slow down bacteria and calm inflammation. But the shunt is basically a detour from that usual process. And so that's been then implicated in Ron Davis's work. He said this whole process is implicated in sort of the development of ME. I don't know an awful lot about it, I'll be completely honest. So this question is definitely a bit above my head. But I'm sure, I think when we've got these hypotheses, Klaus, there's going to probably be some overlap between what Ron Davis's theories are, what your theories are, and the truth will be somewhere in the middle, I'm sure.
It requires a lot of inflammation in cytokines, so it could well play a role in the beginning and make the first hit, for instance, also in the muscle. If it were present in the muscle, you would have more anaerobic metabolism, and this could be the starting point. But it requires a high level of inflammation, cytokines, which are not present in ME/CFS. There may be cytokines may be elevated, but at a relatively moderate level, so it cannot explain a continuous importance of this shunt. Maybe as as triggering in the beginning, setting the first point.
Yeah, absolutely. No one's looked at it, I think, is the answer. We don't really know yet. All of this research is in such early sort of stages. Go on, Helen, next.
No, I was just going to say it's really important to reiterate that as well. It's been so neglected for such a ridiculously long period of time. And speaking as a patient, we are so thankful that work is happening now. But of course, for that to happen safely, it's going to take more time, and it is infuriating, but it is so important that it is done safely. So we all want answers now, but of course we can't have all the answers now because we can't research everything all at the same time without the funding there, and it's catch-22. But yeah, no, sessions like this are so important to understand what is happening. So thank you for that.
Am I all right just to pop up Fraser Moore's comments? I think I just completely agree that in people with ME, GET is absolutely not recommended under any circumstances, and followed up by the NICE guidelines very clear on this. I think where things have got conflated in the past is there might be some people who are a bit burnt out because they've been working too hard and they've been slapped a diagnosis of CFS, and maybe they have got a bit better with some counselling and some graded exercise, but because they get lumped together with patients with sort of genuine pathophysiological ME, you've got these studies that go, we will actually get works in some patients. But completely agree, Fraser. Thank you for clarifying that. We will say that very strongly, that GET is absolutely not recommended, and we're certainly not saying that it should be used at all in patients with ME. Okay, next question, Helen.
Absolutely. I just wanted to do a quick apology. We are having some tech issues this week, which we haven't had before. But if you are watching on your mobile phone, I am aware that some people can only see part of the screen. So apologies for that. Hopefully you're able to listen perfectly, as far as I'm aware. So at least that is okay. We'll have it sorted.
StreamYard have done some updates, and of course it had to be the week where my technical guy is not around, so that's we'll have it sorted for the next one, definitely. Okay.
So so I'm it means I'm having to be quite far away from the screen, and I'm really struggling to read, actually. So
don't worry. I'll pop some questions up. So Michael has asked, can you recover if you would have no PEM for a very long time, or is the pathological mechanism still there?
I mean, the situation can certainly improve. There is you have to first stop the mitochondrial damage, then the mitochondria can recover spontaneously. But of course, you have risk factors, and the question is how dominant these risk factors are. I mean, if they're very dominant, you would probably not totally recover. You would feel better, maybe get from severe to mild or from moderate to mild. But if this mechanism is still operative, you would always have the risk of relapsing if you wouldn't be cautious. So clearly, I think there's a recovery, and our drug would also do this. They would stop the damage, and then the mitochondria would have to recover spontaneously. And this of course, this can take time, and the more damage there is, the more time it takes, and the less mitochondria there are, the more time it takes for recovery.
And I think that fits with my clinical experience. I'm definitely seeing some people get better, and it takes 18 months, 2 years if they've been quite severely affected. It's very slow. It's very, very gradual. It takes huge amounts of effort with pacing and then support in other ways. But I sort of see recovery from ME almost like a 33 piece jigsaw puzzle, and probably many more pieces than that, where, you know, there might be what else is going on, what's going on with diet, what's going on with stress levels, what's going on with external things in people's lives, what's breathing pattern like, what's sleep like, what, you know, so there's all of these different things that fit together. And what's the gut microbiome like? And when you create that landscape where the body is less inflamed by addressing all of these other things, that also helps promote healing in the cells. So I think just thinking about the mitochondria in isolation doesn't work. Like Klaus has said, there's risk factors, there's other things going on, but I'm definitely seeing mitochondria that have been severely affected, people who've been bedbound for months who are recovering with the right support. And
their blood vessel changes, their basement membrane thickening, and things like that do not disappear rapidly. This really takes time to resolve. This needs chronic recovery. So maybe mitochondria can functionally recover relatively quickly, but the number of mitochondria has to rise again, and the mitochondria divide like bacteria divide. So in principle they can recover, but it depends on how much of intact of the mitochondrial biomass you have, and it also takes time for the blood to remodel again, to get healthy blood vessels again. This is this is a question of months or a year or so until the blood vessels would completely recover.
And Klaus, what's your... Sorry, Helen, go on. You
go for it. No, go for it, honestly.
Okay, I was just going to ask about very severe ME, because I have a cohort of patients who are extremely severely affected and tube fed and lying in dark rooms, unable to really move out of their bed at all, even to go to the bathroom. What's your thoughts on what's going on at that really severe end of the spectrum? I know you probably haven't been able to study that group of patients, have you?
No, but I have published a paper on the severe patient and what their skeletal muscle situation is. So I think that the skeletal muscle is, it's not only the mitochondrial dysfunction, but at a certain point of time, the excitation of the muscle doesn't work again because of the sodium pump doesn't work, and it sets the membrane potential, which is so important for excitation. So now we call it the muscle is depolarized. So there's a lack of force, and there's also fasciculation, cramps, and tremor, and this is everything is related. And this is then due also to a sodium pump which doesn't work properly. So the sodium pump does, in the end, it also causes muscle weakness, and it also causes the mitochondrial damage indirectly because sodium rises, and with sodium calcium rises. So this is all these things are related. But I think we can also explain the situation of the severely ill, that the patients don't have any force anymore.
Yeah, so just to translate that a little bit, it's taking me, really challenging me going back to my medical school days now about how muscles contract and the mechanisms, but you have sort of muscle fibers that have to slide over each other and contract to make muscles work. And that relies on electrical changes across the skeletal muscle. And what you're saying is when the mitochondria are really damaged and the sodium calcium levels are, very abnormal, is saying that it can actually affect the ability of the muscles to actually contract because it changes those electrical potentials.
Yeah. It's the beta-2 receptor does stimulate the sodium pump, and if it is not stimulated, the membrane potential gets more positive, then the excitability decreases. The true excitability
lose their ability to sort of contract then.
And the sodium pump is inhibited from reactive oxygen species that are generated by mitochondrial dysfunction. So mitochondrial dysfunction impairs the sodium pump even more. It's not stimulated enough because of the deficit of the beta-2 receptor. And then it's inhibited. It requires a lot of ATP, a lot of energy, but the mitochondria don't produce the energy anymore with mitochondrial dysfunction, and they produce reactive oxygen species, abbreviated as ROS, and the ROS inhibits the pump. So the pump doesn't work, and then it doesn't generate an appropriate action potential, and without an appropriate action potential, there is no excitability, no good excitability, which means no force. So there's a lack of force.
So is that the reason behind, for example, upon waking up, some patients have paralysis? I know I've experienced that. Or is that a different condition, which is part of the umbrella of chronic illness?
It's simply an aggravation of the situation. It's a situation of the severely ill patient. So at the first stage of dysfunction of this pump and the ion transport, you have this mitochondrial dysfunction, and then this depolarization develops with the loss of force. So it's only a continuation of the disturbances. It's nothing new.
I think paralysis is probably temporary paralysis, probably something different, Helen. I think this is a bit more of a. It's a bit more.
Some patients have ionic disturbances of the sodium or potassium channels. So this may be other influences with true paralysis. I saw a few patients. Was come by a few patients that have hyperkalemic or the hypokalemic disturbances, skeletal muscle, and I think they also get sodium overload by a different mechanism, by the sodium channel itself, not by the sodium, not by the sodium protein exchanger. So I think these are different risk factors.
It's difficult.
So if you have group paralysis, it's probably a different cause of the disease, and one of these rare channelopathy of muscle ion channels.
Fair.
Yeah.
I was going to ask. Oh,
go on, Helen. Go on.
I'll go for it this time. 626. Before the drug your company is developing becomes available, which treatment/supplements would you recommend to support mitochondria in LC patients? And thanks so much for your inspirational work. This is something that comes up almost every week. I know it's an impossible question to ask, and so it's not a do this question at all, because we're not giving guidance. That would be potentially dangerous. But what might you look at?
I think the main point is all these supplements could work if you abolished the damage, but the damaging mechanism is so strong that these supplements don't have a real good effect. I don't know, so many patients take these supplements, but does this really lead to an improvement? I don't think so. I mean, we lack really regular good studies to answer these questions. I have really no answer to it. But I think the main problem is that as long as the damaging mechanism is operative, all these things that could really otherwise help a little bit have almost no effect.
Yeah, I think the whole supplement issue is so difficult because we just don't have any intelligent way that people can really know if they need the supplements or not. It's just this blunderbuss approach to let's just take this and this and this and this with very crude kind of tests. So I can't think of a better analogy at the moment, but really what you'd want to do is get somebody's blood and kind of mine it for all the minerals, and and you want to know what's in the cells, what's not getting into the cells, and how does it compare to what a healthy landscape looks like. And then you'd want something really bespoke, kind of prepared for that patient. But we're just so far off having any of that. I mean, I think the technology all probably exists, but just the research hasn't been done. So
I think another issue is that there are some people who do promise exactly that to patients, but there isn't the quality control, I've forgotten the word, the regulation. So, it can potentially be dangerous. And so that is always worth remembering for any patients looking for answers, because we all want the answers, but safeguarding is so important as well.
It's an interesting question, and what's a concept I haven't really thought about before: mitochondrial transplantations. So, in a sort of a stem cell sort of way, could replenishing mitochondria somehow through transplanting healthy mitochondria. Is that something that's even possible?
Yeah, of course, it's a theoretical possibility to transplant mitochondria. They're taken up by the tissue. But I think we first need biopsy from muscles and to really judge the mitochondrial situation, particularly in the severely ill patient. We don't have the biopsies. We need them to judge, to see where they are with their mitochondria. And I think transplantation could be the final treatment in the future. Suppose the mitochondria severely patients are really so damaged that they cannot recover, then this would be the last option. But this is not excluded. I mean, it's a possibility, but I would say only for the most severe patients, because first you have to stop the damage. And when you stop the damage, if you have enough mitochondria, they could recover. But if the patient were maybe 10, 20 years in MECFs, I don't know what's left. I mean, nobody knows it. We need to know it. We have to perform the muscle biopsies and to perform electron microscopy of this muscle biopsy to recognize the mitochondrial state of these patients. But in the end, it's a possibility of healing patients that are sick for, let's say, decades.
Yeah, and I think Rob Lust is doing some really exciting work looking at muscle biopsies and looking at doing exactly that, looking at stuff under the electron microscope. And we did a session with him recently. If anyone's interested in watching that, it was really, really interesting work he's doing. Okay, Helen, any other questions you wanted to bring up? I think.
Yeah. So it's not come through here. It came through direct. It was a question about gadgets that basically activate the muscles. So whether that's there's various different ones. Do you know what I'm referring to? Either they can be vibration or they can be to contract the muscles. Generally they're for weight loss. But in a chronic illness capacity, do you have any knowledge of any usefulness around
it would also cause muscle workload. The muscle would have to work, and it's not different from spontaneous work. So electrical stimulated work is the same as there's no difference.
Yeah, thank you.
So it's a really good question from Marco. So who's read the hypothesis, which is great. So I think he's referring to some studies, that Carmen Scheibenbogen is leading on. I'm assuming you're referring to her work, Marco, on immunoabsorption, which is a kind of a way of mopping up autoantibodies. So for people who've got these beta-2 adrenoreceptor antibodies, you can actually, wash their blood sort of with this sort of, stuff that will just remove the autoantibodies. And she's doing a study where she's doing this, but also what we call a sham control, where patients also have a procedure, but they're not getting the immunoabsorption. So you compare. So I think the question is saying that if the immunoabsorption studies are negative, there's no benefit over the sort of the fake intervention, would that discredit this hypothesis of the beta adrenergic receptor antibody being important?
If you could really effectively eliminate all the antibodies, and if you would be sure that these antibodies are pathological, then this would be right, this conclusion. But Carmen Scheibenbogen said she sees efficacy in a subgroup, and she sees a pattern of markers that determine this. So I think the better way, more effective, is these new treatments, these immune modulators, rituximab or daratumumab, and then we will see, because these are effectively remove the autoantibodies. I mean, all these treatments do not totally remove these autoantibodies, and then if you remove them, part of them, it takes time. And for instance, the autoantibodies are reduced if you remove them by apheresis. They are they are generated again, and so the question is always, are you sure that they're effectively removed? And not all autoantibodies are pathological. So we know that there are at least half of the have no autoantibodies. And I think also in some patients with autoantibodies, they not all need to be pathological. They can bind the receptor in a position where it doesn't harm the receptor.
So just to clarify that, not everyone has the receptors. Not everybody, even if they do have them, have the nasty ones that actually interfere with the function of the blood vessels. So, and what Carmen Scheibenbogen is finding is that it's a subgroup of patients who respond. Like everything in ME, you're going to have some people who respond to the treatment, some people who don't. So I think we always go back to this point that you've got to phenotype these patients. You've got to really characterize them really well so we can work out, well, actually, which patients are going to benefit from the immunoabsorption. Because if you just shove everybody in sort of willy-nilly, you might get negative studies.
Another important point to make, I mean, the beta receptor is not, or 2 receptor is not only disturbed by autoantibodies, it's highly sensitive to desensitization, that when the receptor is stimulated all the time, it disappears, it's no more there. And this is perhaps more important because in MECFs there's a high level of stress, always, all the time. And this desensitizes these receptors, makes them ineffective. We know this from, for instance, from heart failure. In these beta-2 receptors also can disappear, or we know it from experimental medicine that this receptor is so sensitive for desensitization. So with a lot of stress all the time, the receptor disappears. And so this could even be more important than these autoantibodies, and this could explain in the other patients. I said it's not, there are many antibodies, but the beta-2 receptor antibody is probably perhaps the most important one, I would say. But there are others, and it's not a single autoantibodies. I think you always need few antibodies to develop the disease.
Yeah, and we see it in asthma as well. So because the blue inhaler, that's what it acts on. It acts on beta-2 receptors in the lung, but it stimulates them. It's not blocking them, it's stimulating them. But if people overuse their blue inhaler and too much, you can actually desensitize the receptors and it stops working. So ironically, the more they take, the less effective it becomes. So Marco had almost preempted that whole thing. Well done, Marco, with this follow-up question.
This is why stress reduction is so important. And the biggest stressor is orthostatic stress, because it's already present when you're sitting, or even severe patients when they move a little bit in the reading position, then they have also cerebral blood flow is already decreased. And this is the stressor. The stressor is the decrease in the fall in cerebral blood flow. And this desensitizes then these receptors.
Yeah, so people who've got POTS and they struggle to maintain their blood flow to the brain against gravity, that's what we call orthostatic stress. So even just them sitting up out of bed or getting up to go to the bathroom, that's creating this stress that could be affecting the function of those receptors. There's so many kind of vicious circles. And that's why, you know, part of the treatment pathway has to be getting really good control of POTS, getting really good control of any external stress, reducing inflammation in whatever way you can, like reducing stress from having an abnormal breathing pattern. All of these things can impact physiology.
And it's not only POTS, there are 3 manifestations of orthostatic dysfunction. There can be hypotension without tachycardia, and there can be no change in blood pressure or heart rate, no significant change, but cerebral blood flow is reduced. And this is the stressor. So you can have a normal response, apparently normal response, but if you measured cerebral blood flow, you would see the decrease, and this is the stressor. So we can't say that you have no orthostatic stress because you have no POTS. Almost all patients have this fall in cerebral blood flow. So all have the stress, the orthostatic stress.
Yeah, it's really interesting, that concept of standing up, and you know, so the patients who do have a drop in blood pressure and some tachycardia, at least we can measure that. But you're saying that there's also a group of patients who don't have the blood pressure heart rate changes, but the blood flow to the brain is reduced, and that puts stress on the system. And that's, I think there is some really interesting technologies that are sort of out there now, you know, this little thing that goes behind the ear that can start measuring cerebral blood flow that people are playing around with at the moment. So we're starting to develop readily available tech. I think in a few years those things will be quite readily available, and people will be able to use them and see whether this is a problem. But then the question is, what do we do about it, you know? So but there's more questions coming in now. I think we're now stimulating a bit more discussion. Let me have a look.
It's really interesting. It's knowing what type of MECFS you've got is just so crucial, and having that diagnostic tool available to get a treatment plan is very clear.
So Columba's just asked about if there's any available tests. I'm assuming, Columba, you mean to look for the sodium calcium issue. Unfortunately not. It's all experimental in research in labs at the moment. So maybe that's something, Klaus, you can develop in time, some sort of clinical surrogate marker of intracellular calcium. We'd love that.
No, I mean, sodium, the rise in sodium skeletal muscle has been measured with radioactive sodium, but it's a really very difficult scientific measure. But measuring calcium overload is very difficult in a patient. It's almost impossible with all the technology, because calcium is so low in the cell with outside. So there's a 1,000-fold difference. So you cannot distinguish between intracellular and extracellular calcium.
Okay, I think we'll finish with this one. So just some recent studies have suggested, so, you know, there's this sort of concept that in ME, the nervous system is always stuck in fight or flight and is stuck in this sympathetic drive. But on the converse, it could be that the nervous system is not able to mount an adequate sympathetic response. That's been proposed in a couple of recent studies. I suspect both things are true for different patients, but is this something you've looked at, Klaus, or have thoughts on?
I think it's true. It's too high at rest, and therefore it cannot recover anymore, and it cannot mount to an adequate sympathetic response that would be needed. And the need is higher than in healthy people, because you have this orthostatic problems, and you also to be able to perform muscle work, you need a higher level of stimulation because of the lack of energy. So it's very likely that the level of sympathy is always too high, and the system cannot recover, and therefore it cannot raise its activity adequately because it's exhausted.
Yeah, and also that idea of desensitizing. Sorry.
There are indications for this. For instance, there is also chronotropic incompetence. The heart rate cannot rise really to the extent what you would expect. So there are some indications that this is really true. But it's always too high, but it cannot mount to the level that would be needed for performing work.
So it's almost like the baseline. The baseline is wrong. There's this kind of false
baseline. Is
baseline.
too high, much too high, and exercise doing muscle work, it's not sufficient. It's insufficient.
But a quick reminder that even laying in bed, listening to bilateral music, humming, things like that can stimulate the vagus nerve, and a lot of people do find help from that, but it's trial and error.
There is indication that not only the noradrenergic system is disturbed, but other neurotransmitters. So there's an imbalance of excitatory transmitters, stimulatory, over the inhibitory ones, for instance, GABA. And so there's disturbance of serotonin, there's glutamate receptors, and histamine is an excitatory transmitter. And it also seems that the GABA system is disturbed.
So all these kind of chemicals that stimulate that fight or flight are floating around in excess, and everything's imbalanced.
At the expense of the inhibition. There's too much excitation day and night, too much excitatory influences, and this is due to autoantibodies, orthostatic stress, stressful situations, and the disease itself, because this disturbance in skeletal muscle, and they then lead to a higher level of sympathetic activity, and so there's a lot of vicious cycles that reinforce the excitation over the inhibition, and it's also the cause for the sleep disturbances, and also for the hypersensitivities. I'm writing a new manuscript on the neurotransmitter imbalance, and which is disturbed by, and I also describe the possible influences.
It makes so much sense of the importance of having complete blackness when you're sleeping, and as little noise as possible, and anything that you can do to help, even if it's only a little bit, they can all add up and help. It's hard to remember.
And the treatment is in principle, I call it a rebalancing treatment. We have all the drugs we are using are in favor of the inhibit the excitatory, whatever you think, and for instance, the GABA agonists, lorazepam and so on, they stimulate the inhibitory ones. So This is kind of
calming things down.
An attempt to rebalance the disturbed neurotransmitter balance.
Yeah. Now, a question that didn't get asked, but I thought would get asked, and we just briefly talked about it before, was about people taking sodium in as part of their POTS treatment. Very quickly, it doesn't affect your intracellular, the sodium pump, and it, you know, the skeletal muscle is sort of quite separate from what's going on in the, you know, with the blood volume, which is what you're trying to increase with salt. So don't freak out about taking your salt tablets after watching this session. It shouldn't matter. If you just follow the advice of your doctor, whatever you've been told. So I think that that's it for tonight, and that's the last session of the year. I'll be back in January. We're not going to have a real sciencey session next time, you might be glad to hear, but we're going to be talking to Jessica Dove, who's founded the Turn2 app, which is an app which really helps you navigate the minefield of all the information and the studies and everything. So we've got her in January, and then in February we have Andrew Klein, and we're going to be talking about B12. So watch out for those on socials, and it just remains to say have a lovely Christmas to anyone who's celebrating, anyone who's really sick. Hope you can try and enjoy yourself a little bit over the festive season, and a massive thank you to Helen today, and also to our guest Professor Wirth. Thank you so much, and we'll see you in the new year.
And if I could just say as well, for anyone who wants to, don't forget that there is support available at all times. You can always reach out. I know it can be a really lonely illness for a lot of people, especially at times of year when celebrations are very busy and not accessible. So don't forget, there is the Facebook group, the Long COVID support, that you can reach out to, and there are so many offshoots as well. So you're not alone, and keep fighting, because there is support, and there is a lot of wonderful people, as you can see right here, who are working hard to get the answers. So thank you, and yeah, we'll get there.
Good night, everyone. Bye.
Bye.